Welcome to the ACE in Action demo, a smart DBMS Bufferpool for SSDs. In this work, we demonstrate how asymmetry and concurrency-aware storage management improves Bufferpool performance. The Bufferpool is a part of database management system that interacts directly with storage devices. The Bufferpool keeps in memory a set of pages to minimize the number of slow disk accesses. Once a page request comes in, the buffer pool is checked to see if the requested page already exists in the buffer pool. In that case, the request can be served immediately. Otherwise, the requested page has to be fetched from the disk and placed in the buffer pool. If the buffer pool is full, then the page replacement policy identifies the page that needs to be evicted from the buffer pool. And if the selected page is dirty, then it is written back to the storage device. Previous Bufferpool managers were designed for HDDs that allow one I/O at a time, and reads and writes have the same cost. However, over time, SSDs have replaced HDDs due to their superior random access performance. However, to take full advantage of the SSD's capabilities, applications need to account for SSD's properties like read-write asymmetry, where writes are slower than reads, and access concurrency, where multiple IOs can be executed in parallel to saturate the device bandwidth. When writing dirty pages to disk, state-of-the-art Bufferpool managers write one page at a time, hence missing the opportunity to exploit the device concurrency. Also, page replacement policies generally do not consider device asymmetry. Instead, they treat read and write requests equally. So, how can we exploit concurrency and offset asymmetry in the Bufferpool manager? Recent research has proposed ACE, new flash-friendly design that improves the Bufferpool performance. ACE uses asymmetry and concurrency-aware write-back and eviction policies. The write-back policy always writes multiple pages concurrently, hence amortizing the write cost. The eviction policy evicts one or multiple pages at the same time from the buffer pool to enable prefetching. When multiple pages are evicted at once, ACE can concurrently prefetch pages to exploit the device read concurrency. Now let's look at the example where the device concurrency is 3 and the write request comes in for page 1. Since page 1 is not in the buffer pool, LRU policy identifies the least recently used page for eviction, that is 4 in this case. 4 is evicted and page 1 is added to the buffer pool. In case of ACE LRU, still LRU policy is used to identify the candidate page for eviction, which is 4. But since the concurrency of the device is 3 and the write-back is initiated anyway, ACE will concurrently write back 3 dirty pages, that is 4, 5, and 2. And page 4 is still evicted from the buffer pool to make space for page 1. At the end, we get similar buffer pool states as in case of LRU. The difference is that ACE exploited the device parallelism by concurrently writing back dirty pages. Now, I will demonstrate the interface that allows the users to compare several page replacement policies with ACE side by side. First, the users will configure the workload parameters and the device properties from the input panel. To configure the device properties, the users can set the base latency of the SSD, which refers to the random read latency. They can also configure the device size, the read-write asymmetry, and the concurrency of the SSD. Concurrency here refers to how many write operations the SSD can perform at the same time without harming the latency. Additionally, the users can set the buffer size and select one of the page replacement algorithms supported by the interface, that is LRU, CFLRU, and LRU-WSR. The users can also configure the number of operations in the workload and set the read-write ratio by configuring the read percentage. They can also configure the skewness of the workload. In this case, 80% of the operations will target 15% of the data. In addition to manually configuring the parameters of the workload, they can also select one of the pre-configured workloads, such as small buffer, large buffer, read-heavy, write-heavy, very skewed, and uniform. If the users select large buffer, the buffer size will be set to 250. If they select read-heavy workload, the read percentage will be set to 90. As for write-heavy workload, read percentage will be set to 20, and so on. Let's say for this simulation, we select a small buffer. In addition to automatically configuring the workload parameters, the users can also select one of the pre-configured devices, such as PCI, SATA, Optane, and Virtual. Finally, once the users configure the input panel, they can start the simulation from the control panel. The control panel allows the users to start and pause the simulation and adjust speed between fast, medium, and slow settings. The users can also finish the simulation and track the progress of the animation from the progress bar. The left side shows the system that uses classical page replacement policy, such as LRU, and on the right, the animation displays the system that is using ACE on top of LRU. Now, if we pause before the first write-back is initiated, we can observe that both LRU and ACE LRU have similar buffer pool states. Now, let's take a single step until first 30 page needs to be written back. In this case, LRU will write back one dirty page. As for ACE, since the write back is needed and the concurrency of the SSD is set to 6, it will write back 6 dirty pages. This way, ACE maximizes the write concurrency and allows the subsequent evictions to target clean pages that do not require expensive write back. Notice that as we continue the simulation, LRU will also write back these dirty pages, but doing so one page at a time. Finally, to compare the performance of the page replacement policies, we have several metrics in the performance panel. For instance, number of disk pages written shows that ACE slightly increases the number of disk page writes. ACE does not increase the disk page reads, and buffer hits and misses are also similar to the LRU policy. However, number of write batches show that ACE issues significantly less writes and also improves the latency because it's fully exploiting the device concurrency. The users can also observe this trend through plots that get updated in real time. The users can also hover over the plots to see the exact values of the experiment. Finally, the users can run the comparative analysis experiments, where we experiment with different read-write ratios and various buffer pool sizes. The users can manually configure the workload parameters and the device configuration, or select one of the pre-configured workloads or pre-configured SSDs. The first plot here shows the results when we experiment with different read-write ratios. The users can also hover over the plot to see the exact values of the experiment. As we see, ACE consistently outperforms the classical page replacement policies. However, ACE benefits are more prominent when the write ratio is higher, since ACE is fully exploiting the SSD concurrency. In our next experiment, we observe that ACE outperforms the classical page replacement policies across wide range of buffer pool sizes. However, we see greater benefits of ACE for smaller buffer pools, since small buffer pool causes more evictions, hence more writes. However, we see that ACE provides benefits for larger buffer pools as well. In our last experiment, we highlight the impact of device asymmetry on various policies. We test LRU and ACE LRU on emulated devices that have asymmetry ranging between 1.1 and 3.0. We normalize the emulated latency of ACE LRU with respect to the baseline LRU. As the figure shows, when we use ACE, the performance gain is higher for devices with higher asymmetry. This is because amortizing the asymmetric write cost is greater for such devices. However, as we see, ACE provides gains for lower asymmetry devices too. Overall, as we demonstrated, ACE improves the SSD utilization by maximizing the concurrency and amortizing the asymmetric read-write cost. Key advantage of ACE is that it can be integrated with any existing page replacement policy with low engineering effort, while any prefetching technique can also be integrated, essentially allowing any existing buffer pool manager to be augmented by our approach. And this concludes our demo of ACE. Thank you for listening.